The roundup rule, specifically 240.4, does not apply to conductors that have been derated. To understand why, it's crucial to grasp the purpose and limitations of 240.4 and how derating affects a conductor's ampacity. 240.4, titled Rounding of Conductor Ampacities, provides a specific allowance within the National Electrical Code, or NEC, for situations where a conductor's ampacity doesn't precisely match a standard overcurrent protection device, or OCT, rating. This rule exists to accommodate the practical realities of conductor manufacturing and OCT availability. It states that if a conductor's ampacity, after all applicable adjustments and corrections, doesn't correspond to a standard OCT size, you are permitted to use the next higher standard OCT rating, provided certain conditions are met. These conditions are primarily focused on ensuring the conductor is adequately protected against overcurrent. The key here is that 240.4 applies to standard ampacity values. These are the ampacities listed in the NEC tables, such as Table 310.15b16, which provide the allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius through 90 degrees Celsius in free air and various raceway or cable configurations. These tables assume specific installation conditions. For example, Table 310.15b16 is based on not more than 3 current-carrying conductors in a raceway or cable or earth directly buried, with an ambient temperature specified in the table. When these standard installation conditions aren't met, the NEC requires adjustments or corrections to the conductor's ampacity. This is where derating comes into play. Derating is the process of reducing a conductor's allowable ampacity to account for factors that increase its operating temperature. Common causes of derating include firstly high ambient temperatures. If the surrounding temperature is higher than the temperature rating of the conductor's insulation, the conductor's ampacity must be reduced. Secondly, multiple current-carrying conductors in a raceway or cable. When multiple conductors carrying current are bundled together, the heat generated by each conductor can raise the overall temperature, requiring a reduction in ampacity. Thirdly, continuous loads. If a conductor is supplying a load that operates continuously for 3 hours or more, its ampacity must be derated to prevent overheating. The NEC provides specific tables and formulas for calculating derating factors. For example, Table 310.15 provides adjustment factors for the number of current-carrying conductors in a raceway or cable. These factors are multipliers that reduce the allowable ampacity based on the number of conductors. Once a conductor's ampacity has been derated, it's no longer considered a standard ampacity value. It's a reduced ampacity that reflects the specific installation conditions. This is where the limitation of 240.4 becomes clear. 240.4 is intended to address minor discrepancies between standard ampacity values and standard OCT ratings. It's not intended to allow the use of larger OCTs to compensate for significant reductions in ampacity due to derating. To illustrate this, consider the example provided. You have number 14, a WGNM cable with 10 current-carrying conductors bundled together for more than 24 inches. According to the 90 degrees Celsius column in Table 310.15b16, number 14 AWG wire has an ampacity of 25 amps. However, with 10 current-carrying conductors, a 50% derating factor applies, reducing the ampacity to 12.5 amps. In this scenario, you cannot round up the derated ampacity of 12.5 amps to the next highest standard OCT rating of 15 amps. The reason is that the 12.5 amps value is not a standard ampacity. It's a derated value that reflects the specific installation conditions. Using a 15 amp OCT would violate the NEC requirement to protect conductors at their ampacity. In this case, you would need to use a 10 amp OCT or reduce the number of conductors in the bundle to avoid derating. The NEC provides specific guidelines for overcurrent protection in 240. These guidelines are designed to protect conductors and equipment from overcurrents, which can cause overheating, damage, and even fires. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. The general rule is that conductors must be protected at their ampacity. This means that the opt rating must not exceed the conductor's allowable ampacity. There are some exceptions to this rule, such as the roundup rule in 240.4, but these exceptions are carefully defined and limited. The NEC also provides specific requirements for the selection and installation of opts. These requirements are based on the type of load being served, the characteristics of the electrical system, and the environmental conditions. For example, the NEC specifies different types of circuit breakers for different applications, such as lighting, motor circuits, and sensitive electronic equipment. It's important to select the appropriate opt for the specific application to ensure proper protection. When applying derating factors, it's crucial to follow the NEC guidelines carefully. Incorrectly applying derating factors can lead to undersized conductors, which can overheat and create a fire hazard. It can also lead to nuisance tripping of opts, which can disrupt electrical service. In some cases, it may be more practical to avoid derating altogether by changing the installation method. For example, instead of bundling multiple conductors together, you could install them in separate raceways or use a larger raceway to improve ventilation. You could also use conductors with a higher temperature rating to reduce the need for derating in high ambient temperature environments. In summary, the roundup rule in 240.4 does not apply to conductors that have been derated. Derating reduces a conductor's ampacity below its standard value, and 240.4 only applies to standard ampacity values. When a conductor is derated, it must be protected at its derated ampacity, and the roundup rule cannot be used to justify using a larger opt. Understanding the limitations of 240.4 and the principles of conductor derating is essential for ensuring safe and compliant electrical installations. Always consult the NEC and other relevant standards to ensure that conductors are properly sized and protected. Consider a scenario where you're installing a branch circuit to supply a new lighting fixture in a commercial building. The circuit will run through a conduit in a hot attic space, and the conduit will contain 6 current-carrying conductors. You plan to use number 12 AWG-THHN conductors, which have an ampacity of 30 amps according to table 310.15b16. However, due to the high ambient temperature and the number of conductors in the conduit, you need to apply derating factors. First, let's address the ambient temperature. Suppose the attic temperature is 122 degrees Fahrenheit, which is 50 degrees Celsius. According to table 310.15b2, the correction factor for THHN conductors at this temperature is 0.82. This means you need to multiply the conductor's ampacity by 0.82 to account for the high temperature. Next, let's consider the number of conductors in the conduit. According to table 310.15 current, the adjustment factor for 6 current-carrying conductors in a conduit is 0.80. This means you need to multiply the conductor's ampacity by 0.80 to account for the bundling of conductors. Now let's calculate the derated ampacity of the number 12 AWG-THHN conductors. The initial ampacity is 30 amps. Applying the ambient temperature correction factor of 0.82, the ampacity becomes 30 amps times 0.82, which equals 24.6 amps. Applying the conductor bundling adjustment factor of 0.80, the ampacity becomes 24.6 amps times 0.80, which equals 19.68 amps. Therefore, the derated ampacity of the number 12 AWG-THHN conductors in this scenario is 19.68 amps. Now let's consider the overcurrent protection for the circuit. According to 240.4, conductors must be protected at their ampacity. In this case, the derated ampacity is 19.68 amps. Can you round up to the next higher standard oct rating? The next higher standard oct rating is 20 amps. However, because the ampacity has been derated, you cannot round up to 20 amps. You must use an oct that is rated at or below the derated ampacity of 19.68 amps. In this case, you would need to use a 15 amp circuit breaker to protect the circuit. Using a 20 amp circuit breaker would violate the NEC requirement to protect conductors at their ampacity. It's important to note that this is just one example, and the specific derating factors and opt requirements will vary depending on the specific installation conditions. Always consult the NEC and other relevant standards to ensure that conductors are properly sized and protected. Another critical aspect of conductor ampacity and derating is the impact of voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. When calculating voltage drop, it's important to use the conductor's actual ampacity, not its derated ampacity. This is because voltage drop is determined by the amount of current flowing through the conductor, not the conductor's allowable ampacity. If the voltage drop is excessive, you may need to increase the conductor size to reduce its resistance. In some cases, you may also need to use a voltage regulator to maintain a stable voltage level. Let's consider an example of voltage drop calculation. Suppose you have a 240 volt circuit that is 100 feet long and is supplying a load of 15 amps. You are using number 12 AWG copper conductors. According to the NEC, the resistance of number 12 AWG copper conductors is approximately 1.98 ohms per 1000 feet. To calculate the voltage drop, you can use the following formula: voltage drop equals 2 times the length of the conductor in feet divided by 1000 times the current in amps times the resistance per 1000 feet. In this case, the voltage drop is 2 times 100 feet divided by 1000 times 15 amps times 1.98 ohms per 1000 feet, which equals 5.94 volts. The percentage voltage drop is the voltage drop divided by the source voltage times 100. In this case, the percentage voltage drop is 5.94 volts divided by 240 volts times 100, which equals 2.475%. Since the voltage drop is less than 3%, it is within the NEC recommended limit for branch circuits. However, if the load were increased to 20 amps, the voltage drop would increase to 7.92 volts, and the percentage voltage drop would increase to 3.3%. In this case, you would need to increase the conductor size to reduce the voltage drop. In addition to voltage drop, it's also important to consider the conductor's insulation rating. The insulation rating is the maximum temperature that the conductor's insulation can withstand without degrading. The NEC specifies different insulation ratings for different types of conductors. It's important to select conductors with an insulation rating that is appropriate for the installation environment. For example, if the conductors will be exposed to high temperatures, you should use conductors with a high temperature insulation rating such as THHN or XHHW. If the conductors will be exposed to moisture, you should use conductors with a moisture-resistant insulation rating such as THWN or XHHW. It's also important to protect conductors from physical damage. Conductors can be damaged by abrasion, impact, or exposure to chemicals. The NEC requires that conductors be protected from physical damage by installing them in raceways, such as conduit or cable trays. The type of raceway required depends on the installation environment. For example, if the conductors will be exposed to physical damage, you should use rigid metal conduit or intermediate metal conduit. If the conductors will be installed in a corrosive environment, you should use PVC conduit or fiberglass conduit. When installing conductors in raceways, it's important to follow the NEC fill requirements. The fill requirements specify the maximum number of conductors that can be installed in a raceway of a given size. The fill requirements are designed to prevent overheating of the conductors and to ensure that the conductors can be easily pulled into the raceway. The NEC provides tables that list the fill requirements for different types of raceways and conductors. It's important to consult these tables before installing conductors in raceways. In addition to the NEC, there may be other applicable codes and standards that govern the installation of conductors. These codes and standards may be adopted by state or local governments or by industry organizations. It's important to be aware of these codes and standards and to comply with them when installing conductors. Ensuring safe and compliant electrical installations requires a thorough understanding of conductor ampacity, derating, overcurrent protection, voltage drop, insulation ratings, and raceway requirements. Always consult the NEC and other relevant standards to ensure that conductors are properly sized, protected, and installed. By following these guidelines, you can help prevent electrical hazards and ensure the reliable operation of electrical systems. Let's also discuss the practical implications of these rules in different scenarios. For example, consider a long run of conductors supplying a sensitive electronic load. In this case, voltage drop becomes a critical factor. Even if the conductors are adequately sized for the current, excessive voltage drop can cause the electronic equipment to malfunction. In such situations, it may be necessary to increase the conductor size beyond what is required for ampacity alone to minimize voltage drop. This is a common practice in data centers and other facilities where sensitive electronic equipment is used. Another scenario involves installing conductors in a hazardous location such as a chemical plant or a refinery. In these locations, the NEC requires the use of special wiring methods and equipment to prevent explosions and fires. Conductors must be installed in explosion-proof conduits and fittings, and they must be properly sealed to prevent the ingress of flammable gases or vapors. The ampacity of conductors in hazardous locations must also be carefully considered, as the presence of flammable materials can increase the risk of overheating. In some cases, it may be necessary to use intrinsically safe circuits, which limit the amount of energy that can be released in the event of a fault. Intrinsically safe circuits use specially designed conductors and equipment that are incapable of producing enough energy to ignite a flammable atmosphere. When working with aluminum conductors, it's important to use connectors that are specifically designed for aluminum. Aluminum conductors have a higher coefficient of expansion than copper conductors, and they can also corrode when in contact with dissimilar metals. Aluminum connectors are designed to accommodate the expansion and contraction of aluminum conductors and to prevent corrosion. They are typically made of aluminum or aluminum alloy and are coated with a corrosion-resistant compound. It's also important to use the proper torque when tightening aluminum connectors. Over-tightening can damage the conductor or the connector, while under-tightening can result in a loose connection, which can cause overheating and arcing. The manufacturer's instructions should be followed carefully when installing aluminum connectors. In addition to connectors, it's also important to use the proper tools when working with conductors. Wire strippers should be used to remove insulation from conductors without damaging the conductor itself. Crimping tools should be used to crimp connectors onto conductors to create a secure and reliable connection. Fish tape should be used to pull conductors through raceways. It's important to use high-quality tools that are in good condition to ensure safe and accurate work. When working with electrical systems, it's always important to follow safe work practices. Always to energize circuits before working on them. Use lockout/tagout procedures to prevent accidental energization. Wear appropriate personal protective equipment, such as safety glasses, gloves, and insulated tools. Be aware of your surroundings and avoid contact with energized parts. If you are not qualified to work on electrical systems, do not attempt to do so. Hire a qualified electrician to perform the work. Electrical safety is paramount. Taking the time to understand and follow safe work practices can help prevent accidents and injuries. The principles of conductor ampacity, derating, and overcurrent protection are fundamental to electrical safety. By applying these principles correctly, you can ensure that electrical systems are safe, reliable, and compliant with the NEC and other applicable standards. Remember to always consult the latest edition of the NEC and other relevant standards for the most up-to-date information and requirements. Electrical codes and standards are constantly evolving to reflect new technologies and best practices. Staying informed about these changes is essential for electrical professionals.